In the last class, we had discussed about the different types of microsensors, the overall fundamental behind the microsensors, and about the different microsensing elements which are involved. And we also had a discussion about the overall template for a microsensor, and we discussed about the different microsensor used for micro robotic application, which includes a radiation microsensor, a thermal microsensor, a magnetic microsensor, a mechanical microsensor, and a chemical microsensor. So we also had some discussion about this hot wire anemometer, and then we had a discussion on the materials commonly used and the overall application of this microsensors, and we had a small introduction towards this micro transducer. Now, in the current lecture, so we will be discussing about the different classifications of micro transducers for micro robotic application. So, the first transducer which we will be discussing is a pressure transducer. So, as far as in this pressure transducer is concerned, if we try to look into the overall construction of it, so there is a kind of a diaphragm which is being placed over here. So, this is a kind of a chamber and a diaphragm, and from the diaphragm there is a strain gauge arrangement. Through the strain gauge arrangement, there is the strain gauge is balanced using a Wheatstone bridge. Now, this is a kind of special kind of sensor that alters the pressure force into an electrical signal. So, these transducers are also called as pressure indicators or manometers, or we can also call it as piezometers and transmitters. So, this is ideally called as a kind of a strain gauge based pressure transducer. These transducers are suitable for measuring extraordinarily high and low differential pressures. The differential pressure is the difference in the pressure between any two given points. So, the transducer contains a sensing element, a diaphragm. Any deformation on the diaphragm will cause a change in the resistance of the strain gauge. So, here in this particular case, the diaphragm acts as a sensing element and the strain gauge acts as a transduction element, and the deflection in the strain gauges are appropriately measured using a kind of a Wheatstone bridge by incorporating a Wheatstone bridge and by balancing the Wheatstone bridge. Now, as an extension of this, we can also discuss about a piezoelectric transducer. So, in the lectures related to micromechanics, so we had discussed a lot about the piezoelectric and its applications and the usage of piezoelectric as a sensor as well as a transducer. So, as far as these piezoelectric transducers are concerned, so these piezoelectric transducers is a special kind of sensor, and the main function of this transducer is to convert a mechanical energy into an electrical energy. So, the piezoelectric transducer works with the principle of piezoelectricity. The face of the piezoelectric material is coated with a thin layer of conducting material such as silver, and when the stress has been applied, the ions in the material move towards one conducting surface while moving away from the other. This results in the generation of the charge. This charge is used for calibration of stress. So, the polarity of the produced charge depends upon the direction of the applied stress, and the stress can be applied in two forms as compressive stress and tensile stress. So, some of the key examples include piezoelectronic ultrasonic sensor, and the ultrasonic piezoelectric transducer works on the piezoelectric effect. In this effect, when electricity is applied to a piezoelectric material, it undergoes a physical deformation proportional to the applied charge. In fact, in yesterday's lecture, we have discussed about two different types of configuration of piezoelectric. One is something like when we try to apply a biasing to it, there is going to be a kind of a actuation which exists. On the other end, when we try to apply a load to it, there is going to be a biasing which exhibits over here. So, based on its capability and based on its functionalization, appropriately we can deploy these piezoelectric transducer for different functional related applications. Next, when we try to talk about capacitive transducer, so This is the overall construction of a capacitive transducer. In this capacitive transducer, we have a fixed metal block and a moving tube, and it is connected to an output, and the change in the capacitance, increase or decrease, will give a kind of impact to the displacement. So, a capacitive transducer is a passive transducer that works on the principle of variable capacitance. It contains two conductive plates separated by a dielectric medium, with the capacitance varying due to change in the plate area, distance or dielectric property. This makes it highly suitable for measuring displacement, force and fluid levels. So, the capacitive transducer contains two parallel metal plates separated by a dielectric medium, which can be air as a material, gas or liquid. So, unlike a normal capacitor where the distance between the plate is fixed, so the distance in the capacitive transducer varies. So, the capacitive transducer uses the principle of variable capacitance to convert mechanical movement into an electrical signal. So, the input quantity causes a change in the capacitance, which is directly measured by the transducer. Similarly, so we also have the inductive transducer. So, as far as this inductive transducer is concerned, so when we try to look into the overall construction of it, so we have a core. Over the core, the coil is wounded. There is a meter and an exciter which is available. So, through the meter and the exciter, a kind of a power is getting generated out of it, and the armature movement is taken care over here. So, by giving an appropriate excitation, we can have an armature movement. So, this is a kind of it has a kind of a simple inductance as well as a mutual inductance which exhibits over here. So, as far as in this particular inductive transducer is concerned, the transducer that works on the principle of electromagnetic induction or transduction mechanism, which is called as an inductive transducer. A self-inductance or a mutual inductance is varied to measure required physical quantities like displacement, force, pressure, velocity, torque, acceleration, etc. Example, like in a simple induction transducer, a single coil is used to measure the required parameter. So, the change in the displacement changes the permeability of the flux produced in the circuit, which results in change in the inductance of the coil and the output. The output can be calibrated in terms of measurement, which is to be measured. The circuit of a simple inductance is shown. In mutual inductance, two coils are used for mutual inductance, one for generating excitation and another one for output. So, the voltage difference between two coils depends on the movement of the armature. So, when the armature position is changed by connecting to the movable mechanical element, then the inductance changes. The air gap between the armature and the magnetic material and also the voltage induced in the coil depends on the change in the armature position. Ideally, good part of this particular inductive transducer is it is capable enough in such a way that even we can have a control over the micron displacement. So, this is one advantage of this particular inductive transducer. Now, let us discuss about this ultrasonic transducer. So, ultrasonic transducer is one type of sound related sensor. These transducer sends the signal, electrical signal to the object. Once the signal strikes the object, then it reverts to the transducer. So, in this process, the transducer measures the distance of the object, not by the intensity of the sound. These transducer uses ultrasonic waves for the measurement of few parameters. So, when an electrical signal is applied to this transducer, it vibrates around the specific frequency range and generates a sound wave. So, these sound waves travel wherever any obstacle comes, and these sound waves will reflect the transducer in form of echo. And the end of the transducer, this echo converts into an electrical signal. As far as in this particular case, the sensor sends the ultrasonic pulse at 40 kHz, which travels through the air, and these transducers are better than the infrared sensors because these ultrasonic transducer sensors are not affected by the smoke or by any kind of material. Whereas in the case of lasers or with the case of optical etc., the material property plays a vital role, especially with reference to the reflection or with reference to the transmission. However, with reference to ultrasonic perspective point of view, this is one major advantage which ultrasonic acts, which basically by applying a short pulse, so we can have a reflection which is more focused towards the echo receiving. From the echo received, appropriately we can study. Now, let us discuss some of the materials which is used for these kind of transducers. So, the primary material which is used in most of the transducers is a kind of a piezoelectric ceramic, which are categorized as lead zirconate titanium, which is mostly used due to its high piezoelectric coupling coefficient and ability to manufacture in various shapes. Similarly, when we try to talk about a barium titanate, it is an older piezoelectric ceramics still used in some applications. Now, when we try to talk about quartz, naturally these quartz are a kind of a naturally occurring piezoelectric material often used in high precision applications due to its stability as well as its characteristics. Now, let us discuss about the different applications of microtransducers. So, the transducers used in electromagnetic applications like antennas, magnetic cartridges, Hall effect sensors, disc read and write heads. The electromechanical applications like accelerometers, LVDTs, galvanometers, pressure sensors, load cells, MEMS potentiometer, airflow sensors, linear and rotary potentiometers. As far as an electrochemical perspective point of view, electrochemical application like oxygen sensors, hydrogen sensors, pH meters are some of the examples of these particular microtransducers. So, the transducers are used in electroacoustic application like speakers, piezoelectric crystals, microphones, ultrasonic trans receivers, sonars, etc. The photoelectric application like LED, photodiodes, laser diodes, photoelectric cells, LDR, fluorescent, incandescent lamp and phototransistors are some of the different applications of microtransducers. In addition to this thermoelectric application like thermistors, thermocouple, resistance temperature detectors are some of the key applications of these microtransducers. And radioacoustic application like Geiger-Müller tube, radio transmitters and receivers are some of the example of these microtransducers. Appropriately, while using these microtransducers for micro-robotic application, these kind of subdomains and applications can be referred for relating to its functionality. Now, when we try to talk about this micro sensors and microtransducers, there are various parameters which comes into existence. Okay, so based on the types of parameters and based on the type of the characteristics of an instrument, appropriately we may need to integrate it to achieve the required functionality. So, the integration of a microsensor and a microtransducer into a system is a crucial aspect of modern technology, which enabling a precise sensing, signal conversion and automation. However, they can be typically integrated as, like for example, when we try to talk about the sensor selection, the sensor selection are identified with reference to the different physical parameter which are being employed. It also chooses an appropriate microsensor based on our requirement. It also considered the sensitivity, accuracy and response time for the relevant sensor selections. So, ideally when we try to talk about an instrument, you might have heard about this static characteristics of an instrument and the dynamic characteristics of an instrument. So, as far as static characteristics of an instrument is concerned, the static characteristics is more focused towards kind of it doesn't include the time t into the consideration. Like we may talk about the reproducibility, repeatability, accuracy, precision, resolution, etc. So, these are some of the characteristics which we call it as a static characteristics. However, in the case of a dynamic characteristics, so when we try to include the time t, so when we try to consider the response of the system or an instrument with reference to time t, we call it as a dynamic characteristics of the instrument, which are considered to be one of the key aspect with reference to a sensor selection. Now, when we try to talk about the signal acquisition, So under the signal acquisition, we have a sensing physical change, conversion of the physical change into an electrical signal, then a micro transducer amplifies and conditions the signal based on the requirement. So this sensor should appropriately discuss with the signal, should have an appropriate signal conditioner to create a kind of a different transformations or different parameters to take care of different parametric conditions. So like sensing physical change, etc. Now we can also include the signal processing process. So as far as the signal processing is concerned, so two important aspects which comes into picture, either analog to digital conversion, or in certain cases we also have digital to analog conversion. Second important signal processing characteristics is filtering and noise reduction. In the case of filtering and noise reduction, appropriately we try to filter out the signals and then we go for a noise reduction. Then we can talk about the data interpretation and output. So as far as the data interpretation is concerned, we have a process signal sent to the microcontroller and the data analyzed for decision making, and then there is an output which is displayed. Now we have the last element, which is nothing but the system feedback. So the system feedback and the optimization, it takes care of the requirement as well as it takes care of the overall different parameters, which including the sensor selection, the signal acquisition, the signal processing, the data interpretation and the system feedback. So when we try to talk about the system feedback and optimization, we have three different parameters which contributes. One is called as evaluate system performance, another one is called as adjusting sensor parameter, third is a kind of optimized signal processing technique which is being efficiently deployed for analyzing the system feedback. So overall, if we try to look into the overall aspects of microsensors or micro transducer, these are the different sub parameters which will try to contribute towards the overall integration of the system. Now let us discuss about the optomechatronic system design. So as far as in this sensors and signal conditioning is concerned, like microsensors is concerned, especially for micro robotics, optomechatronic system plays a vital role, since this integration of this optomechatronic system has an impact towards the application in micro robots. One important point with respect to an optomechatronic system is these optomechatronic systems are flexible enough in such a way that the micro robots can easily manipulate the signal based on the requirement or based on the characteristics. Okay, so when we try to talk about an optical system, these optical system has a flexibility for diverting the beam, or for as far as flexible manipulation of the beam or flexible integration of the beam for different requirements. Now when we try to talk about this optomechatronic system design, these optomechatronic system ranges from telescopes to microscopes, from wafer steppers to electron microscopes, from high-end 3D printers to gravitational wave observations systems that are depend on the cutting edge mechanical engineering. So to achieve a balanced design for such complex optical hardware, optomechatronics is a discipline which combines a mechatronics, the design principles, the system engineering and the optics. So optomechatronics is a field that investigates the integration of optical components and technology into mechatronic system. So optical component in these systems are used as a sensor to measure the mechanical quantities such as surface, structure and orientation. And optical sensors are used in feedback loop as a part of a control system in mechatronics devices. Now in addition to this, optomechatronics has an application in areas such as adaptive optics, automation, optofluidic and thin film technology. So overall, if we try to look into the integration, so mechanics and optics join together to form an optomechanic system. Optics and electronics join together to form an optoelectronic system. Mechanics and electronics join together to form a mechatronic system. So the overall interface of all these three, optomechanics, optoelectronics and mechatronics, will result in a new domain which we call it as optomechatronics. Let us see the evolution of this optomechatronic system. So, when we closely observe the evolution of this optomechatronic system, initially the optomechatronic system started with the holography. So, from the holography, so there is a kind of as far as holography process is concerned, most of you might be aware about it. So, these kind of holography process are initially deployed for kind of authentication perspective point of view. So, this is how exactly the holography was taken up into consideration. Next, there is a kind of a fiber optic endoscope which are being established. So, the main function of this fiber optic endoscope is like an optical fiber is integrated for biological related application. Then in 1960s there was an evolution of the helium neon laser, especially the advent of the lasers started coming into picture. The advantages of the lasers were taken up with different applications. So, some of the key laser systems includes helium neon laser, semiconductor lasers, tunable lasers were taken up into consideration. Now, when we try to talk about the measurement perspective point of view, Moyer topography was the first invention which was taken up for an application. Then an optical lithography came into existence. Then there is a kind of a CCD image sensor came into existence. Like slowly the invention of these or the innovation in this optical system has taken up a new shape with reference to development of products, etc., which has led to a kind of a sensor which we call it as an optical fiber sensor. Now today optical fiber sensors are used in communications, it is used for sensing related applications and other related areas, etc. Then we have a kind of an optical display which is being established as far as optical display is concerned. So, it is mainly meant for the optical fiber sensor integrated with optical displays are being established. Then we have an optical communication in place, and then later in due course optoelectronic processors have taken up a good shape. Now we are talking about micro optics, MEMS based micro optics, etc. And there are different formations of these optomechatronic system on from a macro level to a micro level, so that it has spread its own wings for different applications, including biomedical and then more on automobile related applications, etc. Now let us discuss about some of the functional fundamentals or the basic rules of these optical elements. So, as far as these optical elements are concerned, so the major function and role of the optical components or elements in the optomechatronic system can be categorized into several technologies. One is through a data transmission, where we use an optical fiber over here. So, as far as optical fiber is concerned, so to give you a brief overview, so optical fiber has a core and a clad. So, it works on the principle of total internal reflection. So, with reference to total internal reflection, so like when either we stretch the optical fiber or if we bend the optical fiber appropriately, there is going to be a kind of a deviation in the electrical signal. So, let us consider this as a laser source, and then there is a detector which is available. So, the laser source, through the laser source the light is made to get transmitted within the optical fiber, and then there is a detector which is being placed. So, the detector sends the light, and then when there is a kind of a bending which happens appropriately, we can get a kind of a signal which is established over here. Next, in the case of an actuation, so there are different light based polymers or optical based polymers which are available, light sensitive polymers. Polymers are widely used for different applications. So, as far as these light sensitive polymers are concerned, so what does it does is basically we will be having a kind of a tube or a kind of a system, so in which such kind of polymers are embedded, and when a light gets illuminated, so appropriately there will be a kind of a expansion or contraction in these polymers, which will result in a certain amount of actuation in these polymers. So, these illuminations will be highly helpful for appropriate actuation, okay, and then we can see the like overall displacement which exhibits from this particular system. So, here in this particular case, the light source plays a vital role in actuating such kind of systems. Next, when we try to talk about a data display perspective, let us talk about the kind of a sensing perspective point of view. So, in this particular case, let us take an example of an AFM. So, AFM is a very good example of an optomechatronic system which is mainly meant for studying the surface roughness parameters. So, where we will be having a kind of a cantilever. So, over the cantilever we will be having a small mirror and the light will be instanting on this mirror, and the cantilever moves back and forth, and the overall roughness pattern which is being generated on this particular structure is being evaluated by the detector. So, like the overall tunneling effect in the cantilever and the overall deviation in the overall reflection from the mirrors are being appropriately sensed in a particular domain. So, ideally it is a kind of an image acquisition, image processing to study the overall characteristics of the image which is being captured, which is well established. It's a kind of a well established technology. In fact, nano manipulation in an atomic force microscope. So, we have a separate module where we will be discussing about how nano manipulation is happening in an atomic force microscope and how it has an impact towards such kind of precision measurements will be discussed. Now, in this particular case, there are two different parameters which comes into picture. In fact, two different domains which comes into the picture. One domain talks about a kind of a measurement and the other domains talks about the processing. And that is, so identifying a certain mechanism, based on the mechanism. So, when there is a deflection exhibits, from this mechanism we can get the overall image characteristics or the overall output characteristics with reference to deflection or with reference to the images, etc., can be taken care by this optomechatronic system, and then whatever images are captured, these images needs to be processed. So, in order to process this image, so there are several steps are involved, like image restoration, image thresholding, etc. So, many steps, edge deductions. So, these are some kind of different steps which are involved to process this image and to acquire the information which is available in the image. So, this is a kind of a separate study which is being established. Next, we can also talk about in the case of a computing. So, we have a kind of an optical transistor which is available over here. So, this optical transistors use a kind of a nonlinear material, and then it has a reference beam and a probe beam. From this we can estimate the behavior of the material. Next, we have a kind of a data memory like the CD, the Blu-ray disc, etc. So, these are some of the systems which has been established, which also comes under the category of this optomechatronic system. Now, when we try to consider the practical optomechatronic system, so these optomechatronic systems are found in many control and instrumentation, inspection and testing. So, this optical manufacturing, consumers and industrial electronics products as well as in MEMS, especially in the case of automotive, bio applications and many other fields of engineering. So, some of such application includes cameras and motors are the typical that are being operated by optomechatronics components. Like for example, today we are talking about this autofocus. So, in the case of an autofocus, an image is observed, image is captured, then the image is processed. Based on the distortion in the image, so it is mapped with the reference. The distortion is analyzed. Based on the distortion, appropriately the signals are fed into the motor. which is connected to the lens arrangement. Okay. So, this lens will manipulate appropriately to again capture the image. So, this is a kind of an arrangement in which there is a kind of a like an image is taken up, and then the distortion, based on the distortion in the image as well as the based on the distortion in the edges. So, appropriately a signal is fed to a motor which is connected to a focusing optics. The focusing optics adjusts itself to get a better clarity on the image. So, this is one good example of an optomechatronic system. Now, when we try to talk about, when we discuss about the different types of optomechatronic systems, so optomechatronic systems are categorized into three classes depending on the how the optical element and the mechatronic systems are integrated. So, one is called as optomechatronically fused system, another one is called as an optically embedded mechatronic system, and mechatronically embedded optical systems. So, these are the three different classifications which are being efficiently into the practical applications. So, based on these classifications, we have different systems which are being integrated, or there are different wide varieties of applications which are being embedded into the system. Now, when we try to talk about this optomechatronically fused system, as far as in this optomechatronically fused system is concerned, so in this system, optical and mechatronics element are not separable in the sense that if an optical or mechatronics element were removed from the system, the system could not function properly. So, like the system that belongs to their class are auto camera, adaptive mirrors, tunable lasers, CD pickup, optical pressure sensors, etc. So, as far as in this particular case is concerned, we are trying to integrate an optical fused with the main system, like an example of an autofocus is, so the working of an autofocus is one good example where an optomechanically fused system will be taken up. Next, we can talk about the optically embedded mechatronic system. So, as far as this optically embedded mechatronic system is concerned, this system is basically a mechatronic system that is mainly composed of like electronic component. So, in this system, the optical element is embedded on the mechatronics. Like for instance, the optical element is separatable from the system, yet the system can function, but with a decreased level of performance. Example, washers, vacuum cleaners, monitoring and control system for machines for manufacturing, etc. That is like you have a system in place and an optical system will be embedded into it. Now, this optical systems which are being embedded into it takes care of the precision measurement. However, when you try to remove this optical system, so appropriately it tries to disturb the precision measurement based on the variation in the precision measurements. So, like the efficiency of the system may come down. So, that is like this optical system will act as a kind of an element in this system. So, even if you remove this it acts as an accessories in the system. Even if you try to remove it, still the main system work. Now, the third category is called as a mechatronically embedded optical system. This system is basically an optical system whose construction is integrated with mechanical and electrical components. Many optical systems requires a positioning or servoing optical element devices to manipulate and align the beam and control the polarization of the beam. Example, the cameras, optical projectors, galvanometers, series, parallel scanners, line, polygon, etc. So, like in the case of optical projectors, we have a kind of a manipulating mirrors or lenslets of mirrors which are available. So, these kind of systems are called as a mechatronically embedded optical systems. Similarly, a galvanometer which is used for manipulating a laser beam is one good example where a mechatronically embedded optical systems can be deployed for different applications. Now, we will discuss about the different components of optomechatronic system, and we will go one by one how these optomechatronic systems are well established and about the different classifications, their functionality and operation and details in the upcoming classes. Okay.